Hello everyone, this is Brock Skaggs, and we're going to take a look at this step shaft problem that you can see on the screen now. And so a step shaft, what am I talking about? Basically I'm talking about a shaft which is going to have a number of different diameters associated with it. And so here you can see the shaft has three separate diameters, a D1, D2, D3, depending on where you're at along its length there. And the changes between the sections are very discrete, very sudden changes there. It's not like we have a gradual taper where one diameter blends into the other, but it's very step-like, hence the name of step shaft. And so the idea here is I'm basically fixing it to some rigid ceiling here at the very top, and then what I'm going to do is I'll put, before I put it there, I guess put weights on there, or I can somehow clamp the weights around it, I suppose, in order to produce this axial loading at the two different steps. But then I'm also going to take, say, some ropes or some cables, we'll say, and I'm going to pull upward on them, and through the green rigid plate, we'll say at the bottom, apply this kind of axial compressive force associated with the plate itself there. And so some specifics of the problem, you can see the different lengths of the sections there. We'll call section 1 the very top section, section 2 the middle, and section 3 the bottom one. Lengths of 300, 250, and 200 millimeters respectively. Different diameters there, ranging from 15 millimeters at the small end at the top down to 40 millimeters at the big end at the bottom. As far as the material itself of the shaft, we're assuming it's going to be a 1060 aluminum alloy. One thing you can see here with the material properties, 27.6 megapascals for the yield strength, and then also the E value, that is the modulus of elasticity or Young's modulus, essentially a description of the stiffness of the material itself, 69 gigapascals. If you're wondering where I'm getting those values, actually I'm getting them from the SolidWorks 2016 material library there, and so I just looked up the material properties associated with this 1060 alloy. I rounded the yield strength a little bit, but the E value was right at 69 gigapascals. As far as the applied loads go, you can see my top disc there is at 2 kilonewtons, the second larger disc is at 5 kilonewtons, and then I'm assuming that the total upward force associated with the pulling of both of those cables is going to be at 4 kilonewtons there. Alright, so there's the inputs. Now what are we going to do? Well, one thing we're going to do is determine the normal stress experienced by each section of the shaft itself here. And so what's going to happen here is each segment or section of our shaft is going to be carrying a different axial force. And so that's going to create a different normal stress, but also has a different area, which is also going to be a contributor there. This is a axial loading case. We're talking about normal stresses, so hopefully in the back of your mind you're seeing the formula already to get the normal stresses that we're talking about, as the sigma is F over A here, where our F is the force carried by that section of material, and A is the cross-sectional area of the material at that given point as well. And so we have both A changing, as you can easily see by the three different diameter values, and we're also going to use free body diagrams to show that the force carried by each of this section is also going to be changing as well as we walk along the length of the shaft or rod. And so that's task 1. I'll try to get through that during this video. I'll probably make a second video where we'll jump into task 2 and look at the displacement of the green plate, which is basically saying, hey, when these loads are applied to the shaft's going to not remain the same size. It is not going to be perfectly rigid, so it's going to either elongate a little bit or be compressed a little bit, or maybe a little bit of both depending on what section we're looking at. And the green plate's going to move. And so does the green plate move up or down? And how much does it move? Those are basically the question we're asking in task 2 there. But most likely that'll be in a second video. And so let's go ahead and start looking at task 1. Okay, I've got to figure out the normal stress in the middle of each region, in the middle region of each segment, is the way I describe it. And so one thing you might be asking, okay, why is he picking the middle of each segment? So I'm picking like right around in here, right here, right here, basically where the leader's pointing to, we'll say, on each of those diameter notes. And the reason I'm picking the middle is because it's away from any changes in geometry. It's also away from any application points of the loads themselves there, because this simple formula we've got over here, sigma is F over A, may not give correct results in those applications because we're not taking into consideration stress concentrations or stress risers that are subject due to, for instance, the changing geometry in that area, which we'll have to talk about later. And so one thing we can do is figure out the areas of each of those sections. That's fairly easy. We know there's circular cross sections and the diameters. The forces, on the other hand, that's generally where people will mess up in this type of problem. They'll just kind of look at it and say, well, I think that this section, this section, this section has forces X, Y, and Z. Well, the best way to do it in my mind is to always draw free body diagrams, write your equilibrium equations, and then just let the math tell you what the force in each section is there. And so you've got a number of different options inside of free body diagrams. For this problem itself, I'm going to draw a free body diagram first to uncover the force carried by section 3. That's the very bottom section. And so I'll do this all in red. And so I want to know the stress at that cross section right there. So I'm basically drawing the dashed line there and saying, hey, I'm going to cut the material right there. And so I don't really mean take a saw over there and actually cut it, of course, but basically remove this section from the rest of the body for consideration. And the other boundaries of my free body diagram are that I'm going to go all the way to the very bottom of it there, and just like so. And think of me basically removing that chunk of the material after it's been loaded. And so here I'll draw my free body diagram, and we'll call this section 3. Okay, so now we've got to draw some sort of representation of what I removed. Well, there's my cut surface. We'll say there's the very bottom of the shaft itself. And so one thing I'm going to do is I'm going to say, well, I'm trying to figure out the normal stress, so there has to be some internal force that this section is carrying. I'm going to make an assumption that it's in tension. And so the way I'm going to do that is I'm going to draw this force right here. Notice it is perpendicular to the exposed section of the material, or exposed surface of the material that I made with my free body diagram cut, and I'm going to call that F3. And so this is the internal force carried by section 3. Well, are there any externally applied loads to that section? If I look up here, I'm hoping you're saying yes, because here I've got these cables. Notice they go through holes in each of the black weights here. They're attached to the green plate. We're assuming that's going to be rigid. Well, the green plate's basically going to be pushing upward, right, on the bottom section here. And so that upward force associated with the contact between the green plate and the bottom of my step shaft, I'm going to call T because it's through the tension in the cables. And that T value we said was 4 kilonewtons total. So that's equal to my 4 kilonewtons there. And that looks like a complete free body diagram for this section. And so now I'm ready to write my equilibrium equation. And so here I've just really got a 1D problem. I'll say the forces are acting in the y direction, where positive y is upward. And I'll say, well, it's positive F3 plus my T has to equal 0. Because here I'm working this problem under the understanding that it is in static equilibrium. And so here I'll say, well, F3 then has to just equal negative T, which is my negative 4 kilonewtons. And so I obviously know the magnitude here is 4 kilonewtons. The negative sign is indicating that I assumed wrong. And so I initially drew that arrow upward away from the cut section here, which is saying I'm assuming a tension. But the negative sign says, hey, you assumed the wrong direction. This thing's actually in compression. And so now that I know the axial force carried by that segment of my shaft, I can say, well, sigma, I'm going to call it sigma 3 here since it is section 3, is F3 all over A3. And I can work this a little bit farther and say, well, A3, that's a circle, so it's pi over 4, diameter 3 squared. And we can do a little algebra here before we substitute in. We'll say it's 4F3 all over pi times D3 squared. Looking good. And so just a little arithmetic, and now we're ready to start inputting my values. And so I've got 4, this was negative 4,000 newtons. Notice here I'm getting everything back to base units there, so I don't have quite as many unit hurdles to jump through at the end of my problem. D3 here, what was the diameter? I've got it up here as 40 millimeters. And so I'll put in here 40 millimeters, 0.040 meters squared, which gets me here. So 4 times negative 4,000 divided by pi times 0.04 squared. I'm getting at negative 3.18 times 10 to the 6th. That would be in pascals, so I'll write it as negative 3.18 megapascals. Oops, got a little overambitious with my M. Megapascals, there we go. Another thing that you could also write this as, I'll just put here or, I'll write it as 3.18 megapascals, and I'll put a comma C here. Both of these indicating that it's compression. Here I'm just removing the negative side and putting the comma C to indicate compression. The one caveat that I can say about this is you have to be careful about taking the value straight from equilibrium equation here. You can see it says negative 4 kilonewtons right into your stress formula and then computing the value considering the negative sign the entire time. Because remember, this negative sign here on the left in the equilibrium equation all has to do with the assumption I made here. And so that can lead to incorrect results in terms of interpreting something being in tension or compression depending on initial assumptions there. And so you just have to be careful about how you make those assumptions and how you interpret it there. But this first section we're considering, or actually the bottom section, section 3 of our shaft, is in compression, and it has a normal stress of magnitude of roughly 3.18 megapascals. And so now we just need to do that 2 more times in order to figure out the normal stress in the other 2 sections. And so one thing you might do at this point is pause the video, see if you can figure out the stresses in each of the other 2 sections, and then review it the rest of the video to see if you get it correct there. But I'm going to go ahead now and look at section 2. And so section 2, I'm going to go in blue, and here I want to know the normal stress in the middle of section 2. And so I'm going to expose the cross section right in the middle of section 2, just like so. And here, where's my other boundaries of the free body diagram? Well, I'm going to take this all the way down into the exact same boundary that I had for my first free body diagram of section 3 down there. So it's looking just like that. And one of the reasons I keep going all the way down to the very bottom of the shaft is because I don't want to find the reaction force where this thing's attached to the ceiling. And so you can see in blue where my section is I'm going to remove with the free body diagram. And so now I'm going to come down here. This is free body diagram section 2. And so what did I draw? Well, I removed a little bit here. This is the bottom half of segment 2. Then I've got segment 3 sitting below it. Of course, none of this is really to scale. And that's basically the chunk of the shaft that I have. And so now I'm going to assume, hey, there's going to be an axial force in here. I'm going to assume it's in tension again. So this is the unknown axial force carried by section 2. I'll just call it F2. Now, what other externally applied forces are on the shaft here? Well, I'm using the same boundary at the very bottom as the first free body diagram I drew, so I'm still going to have the green rigid plate pushing up on the bottom of the shaft. So I've still got the 4 kilonewtons associated with the tension and the cables there. But we also have to add another force now. And now I go back up here. I'm missing the force associated with this weight, right? That's included in part of my free body diagram. And so we would feel the force of the weight of the disc here, disc number 2, pushing down right at this intersection here. That W2 value is 5 kilonewtons. And so I'll put it right here. It's pushing right there down with a value of W2 at 5 kilonewtons. And so that should complete our free body diagram. Next step, of course, is to write equilibrium equation. So because I got to figure out what that F2 is going to be. And so here, upward is positive, so we'll go F2 minus W2 plus my T is equal to 0 and solve for F2 here. And so that's W2 minus T. W2 is my 5 kilonewtons, my T is 4 kilonewtons. Looks like 5 minus 4, well that's just 1 kilonewton there. And so that's looking good at this point. I've got a axial force of 1 kilonewton carried by this section, and notice it's a positive value this time, so that means my assumption was correct here, and that is indeed in tension. And so here I'll just come over and say, well, sigma 2 is equal to the force in section 2 divided by the area of section 2 here. here I'm basically doing the exact same algebra up to this point here, and so I'm just going to shorten this bit here as far as what I have to write and say, well, that's going to end up equaling 4f2 all over pi times d2 squared. And then I'll just substitute the values. 4 times, again, we'll get back to base units here, so that's 1,000 newtons for the 1 kilonewton, divided by pi times the diameter, and the diameter here was 25 millimeters, so divided by 0.025 meters squared there. And so we've got 4,000 newtons in the numerator divided by pi times 0.025 squared. Gets me right around 2.04 megapascals. So this is carrying a stress of right about 2.04 megapascals, or experiencing a stress of about 2.04 megapascals. I'm going to emphasize here this is tension here just by putting comma T here off to the side here. And so interestingly enough here, you're going to have section 2 here that's going to be getting longer, while section 3 is actually going to be getting shorter here because of the compressive normal stress. And so that is looking good at this point. And so now we're ready to move on to free body diagram number 1, really. And before I go here, I'm going to draw it up here again. We'll use green for this one. And so green will come right here. Go ahead and make my cut here, and we're following the exact same pattern, going all the way to the bottom here, getting that bottom part, and going all the way back up here. And so now we've got more of the step shaft than we did before. And so here I'll come back down, again drawing our free body diagram here of, now it's section 1. And you can see how I've kind of talked about this being very mechanistic here. We're just going through the motions at this point. There's the bottom half of section 1, here's section 2. Excuse my horrific drawing there. And there's section 3 there. Again, let's assume that there's an axial force, non-zero axial force here. And I'm drawing it as being perpendicular to that cut surface, perfectly vertical, or my surface is supposed to be perfectly horizontal. And we'll call it just F1. And now it's a matter of putting the externally applied forces on this section of the shaft. Well, I'm going to have the same ones that are in my second free body diagram here. So I'm including those portions. And so I'm going to have upward T here with 4 kilonewtons. I've got W2 being applied here still with 5 kilonewtons. But now I'm also going to have the first disc. It sits right here, right? Yeah, with W1 there. That's going to be, if I zoom back out, right here. You're going to feel the weight of that first disc in this section. And so W1 is at 2 kilonewtons. Here. So that is looking good. Try not to jostle around too much. And so now let's write some equilibrium equations. And so we'll say, well, still sum of the force on the y. Got positive F1 minus W minus, minus W1 minus W2 plus T has got to equal 0 because we're thinking this is in static equilibrium. And so now solving for F1, it'd be what? W1 plus W2 minus my T. And so I've got W1 plus W2. I'm going to go ahead and shorten that to 7 kilonewtons. Minus my T is 4 kilonewtons. Gets me to 3 kilonewtons there. And so now that I know the axial force here, 3 kilonewtons, notice it's positive, so I assumed correct over here. It actually is in tension, and I can quickly calculate my sigma 3 to wrap up this video. And so sigma 3 here is F3 over A3. We saw that the algebra worked out for this case to 4F3 over pi times D3 squared. Why am I calling them 3s? They should be 1s, right? We'll go ahead and make that change real quick before we all get confused. This is section 1, not section 3. So we'll call this sigma 1 because it's section 1. Here's A1, F1. There we go. Write subscripts now. So this was 3,000 newtons all over pi. And D1. What is D1? We'll come back up here. D1's 15 millimeters. So again, back to base units, 0.015 meters squared. And so I've got 12,000 newtons in the numerator divided by pi times 0.015 squared. Roughly 1.697 times 10 to the 7th, so about 16.98 megapascals here. Again, positive value here, which should be interpreted as intention. So I'll just put comma T off to the side here to further reinforce that value's intention. So at this point, with those three basically lines of work, I've got the normal stress in the first, second, and third working mode from the bottom up here. And one thing we can also do is do this with some software. And so here I'll just pull over my SolidWorks simulation of this problem. And what I've done is I've applied the loads associated with the different weights here, the upward force associated with the contact between the green plate that's getting pulled up by the cables at the bottom. Here's my fixed connection at the top. I'm showing the normal stress plot in the y direction, which you can see by my coordinate system here is the same as before. And I'm just going to probe this thing in the middle of each of these sections. And so using the probe tool there, you can see the values here. One thing you can see is the first top two are positive and the second one, or the third one is negative, showing that the top two are in tension, the third one is in compression, which if I toggle back over to OneNote, we said here's the top two are both in tension, the bottom one's in compression, and then you can also check the values here. For instance, section 1 here, 16.98 megapascals in tension. That's right here, 16.992 megapascals in tension, so very close. Then you've got the middle section, 2.04 megapascals in tension. Here I've got 2.038 megapascals in tension, very close again. And then the last one I've got at 3.18 megapascals in compression. And this is showing negative 3.184 megapascals or 3.184 megapascals in compression. So here we're seeing very good agreement between the numerical approach that we're using with SolidWorks Simulation and the theoretical approach that we just went through. And so hopefully that helps you in understanding how to use free body diagrams to solve for the axial forces in the sections of these step shaft type problems and solving for the normal stresses. Here I'll quit now and then make a second video where we'll look at the displacement of the green plate. As always, thank you for watching the video.